Hello, this is Susie Newhan, and this is the one introducing marginal change and differentiation, because they go together like Ben and Jerry. So the idea of doing something just one more time, the incremental cost or the incremental benefit of doing the next thing. So here's some examples of marginal changes. You may well be familiar with some of these. So marginal cost, the cost of producing just that one extra thing, not taking into account fixed costs or any of that kind of stuff, just the cost of producing one more. Marginal utility. Utility is about satisfaction. So how much extra satisfaction do you get from your third television or your fourth television? The chances are your extra satisfaction is going down over time, isn't it? Marginal tax rate, how much tax you pay on that one extra pound that you earn. So I'm sure this is something you've thought about before, but it's a nice example of marginal cost. I'll let you read it. So economists are really interested in these small incremental changes because they help you make decisions right now. Do I stop production at this point? So we might be interested in the extra benefit, the extra profit for increasing production by one. Should we hire one more worker? And what is the extra utility for buying my third television? And these are all about marginal change. So until we get to know more sophisticated mathematical tools around marginal change, let's have a little look at some numbers from a table. So here's an example of a total cost function, happens to be a quadratic, in fact there it is. And we're looking at the marginal cost of producing one more at various levels of output. Now this is inherent in here is that there's a fixed cost. Well, there's a fixed cost. So before you produce any, you've got a fixed cost of 10. But we're interested in what cost we will incur by producing one more at each of these levels. So the 10 is sort of already passed. So what's the extra cost in going from that level to here? Well, hopefully you can see that it's 3. The marginal cost at that level of producing one more is 3. What is it here? The marginal cost of producing one more here is going to be 7 because it's going to go from 13 to 20, and here it's going to be 11. Right, and so what does this represent? So at any one of these, it represents the rate at which total cost is changing at that level. It's always relative to a certain level of output. So when quantity is 3, the rate at which total cost is changing is 15. So it's the rate of change at a particular point in the curve. Let's look at a revenue. It's also quadratic, but it's an upside down quadratic. And why is revenue often seen like that? Well, it's this notion of you can't keep increasing revenue forever. In order to keep finding new clients to buy your products, at some point you're going to have to reduce the price. And when you start reducing the price, your total revenue actually goes down because it reduces the price for all your clients. So at some point it gets as good as it's going to get, and then it starts degrading. So hopefully you can see that as economists would really like, or business people would particularly like to know when we should stop producing because we're getting less benefit out of it. But anyway, so here's our marginal revenues. So we get no revenue if we don't sell any. So how much marginal revenue do we get if we go from 0 to 1? Well, hopefully you can see that it's 8, and then it's going to be 4. Oh, and then what happens there? Oh, look, if we go, the marginal revenue we get if we go from selling 12 to from selling 2 to selling 3 is 0. And then we start getting negative changes, i.e. we don't want to keep producing at that level. And here it is. What do we see here? Well, we see that at quantities 2, marginal revenue is 0. And we can see it on the total revenue graph by the fact that it's peaking at that point. So we can start seeing some really interesting stuff from marginal changes. And here's one more example, marginal product. With product sort of means output to economists. And again, we can say each of these level, what's the, how much extra can we produce? And here we're exploring labour. So we keep adding another head count and we look at what difference that brings to us. Yeah. So we're holding capital constant because we normally think of production being a function of capital and labour, but here we're holding capital constant, and we're looking at different levels of labour and what change in output we get. And hopefully you can see that the marginal product here, when we go from 0 to 1, is 57. When we go, I've picked the ones that are easy to calculate. If we go from 270, if we go, sorry, from 5 workers to 6 workers, output goes from 270 to 300, and so on and so forth. But what do we notice? We notice at some point that the marginal product is reducing. And look, indeed, we can see that. We can see the classic diminishing returns. And if we plot, so this is total product, but if we plot marginal product, we can see what's happening here. We can see that at some point we get lots of gains from adding another worker, but at some point we get less and less extra benefit from adding workers. So we're sort of doing it more, but enjoying it less. Yeah, so this is what diminishing returns look like when you plot marginal product. Here's what diminishing returns look like if you plot total product. And so different ways of expressing marginal cost. We could say marginal cost. We could say the rate of change of cost at a particular level. We could say the cost of adding one more item at a particular level. We could say the rate at which cost changes as quantity increases by 1. And I write it like that because hopefully you can start to connect that with the linear functions that we looked at. The rate of change of cost with respect to quantity. They all mean the same thing. And very soon you're going to recognize that as another expression of marginal cost, but much more on that later. So rate of change, gradient, and marginal change are actually all the same thing. A quick reminder, when we looked at linear functions, we learnt that gradient is a change in y of a change in x, so that's the case on any curve as well. So change in y, how much y increased, well, between 2 points, how much y increased divided by how much x increased. Or if it's revenue and quantity, how much r increased over how much q increased. So there are various ways of thinking of gradient. We talked about it as a measure of steepness or slope. Economists often use slope instead of steepness. So it's a measure of how steep it is. It's a ratio of the change in R over the change in Q. It's the amount that R changes as Q increases by 1. So that's an important reminder. The rate of change at a given level of Q, rate of change of R at a given level of Q. But here's the important thing. It also means the marginal change of R, because this is a definition of marginal change. So marginal change is really just the gradient. And talking about gradients and curves, we've got very good at finding the gradient of a straight line function, but what do we do if the gradient is not constant, because we're looking at a curve? And here's some curves. Look, we see here the gradient is 0.74, it's positive, it's upward. Here the gradient is negative, all the same curve, but we look at different points and the gradient changes. This is not a straight line, obviously. Oh, look here, that's an interesting one. Actually, this is very interesting. We're going to look at this later. This, here the gradient is equal to 0, because how much is y going up as x increases? Well, y is not going up at all. So that's a 0 gradient, but a very important one. So we can see that the gradient is changing. So we need completely different tools to help us find gradient. Now that we understand that gradient is really important because it indicates marginal change, then we're going to have to up our game and find ways of finding the gradient of a curve. But let's look at an economic curve. Here's total output, production function. And what do we see? We see that as we increase labour, total output's going up, but it starts going up more slowly, because look what's happening to the gradient. The gradient is declining. The level of steepness of the gradient is declining as we add headcount, as we add workers. And remember that gradient equals marginal change. So these gradients actually represent the marginal product of labour, because that has its own special name, marginal change, when we come to production. So we have either marginal product of labour or marginal product of capital, depending on which one we're looking at. But as gradient equals marginal change, then what we're really seeing here is that marginal output is decreasing, even though total output is increasing. Yeah? We're doing it more, but enjoying it less. So what is it all about? Well, we've learned, haven't we, that gradient and marginal change are the same. We've learned that marginal change is really useful to us. And we know all about finding gradients of straight lines, don't we? Because we did a lot of that already. So we should be in good shape. But the problem is, ta-da, how do we do it? Because we've seen that the gradient of the curve keeps changing. So the process of finding the gradient of any point on a curve is differentiation. That's what it's all about. Differentiation comes from a branch of mathematics called calculus. It was invented by Sir Isaac Newton a very long time ago, and also a German person, Leibniz, who we should also acknowledge. Incredibly sophisticated mathematical tool, and I'd like to just give you a sense of it. I'm not going to teach you all how it works. It's very easy to learn how to do, but it's quite complex to understand where it all comes from. I'm going to give you a flavour of it. All right, so there's two branches of calculus. We're not going to do any integration. We're just going to concentrate on differentiation. This is the one that's used mostly by economists. You will use that a little bit if you're looking at consumer surplus area on a graph, but mostly it's differentiation where all the action is. And it's about calculating gradients. Now, we are going to talk about this thing where we use infinitesimally small changes to one of the variables. So we're going to come to that. And very helpful because it unlocks marginal change for any kind of function. But there's quite a mystique about differential calculus because it feels a big step up in your mathematics education. But actually they do, and you will learn to differentiate. So a quick bit of definition here. A tangent line. A tangent is a line that touches the curve at one microscopically tiny area. So it just touches it. And a curve will have an infinite number of tangents because you just nudges along the curve a little bit more and you'll have a different tangent. So if you want to understand a tangent, you've got to know it precisely at the point of the curve that you're interested. Anyway, so that's a tangent. So back to our question, how on earth do we find the gradient when we know that the gradient's changing? Well, one thing we could try and draw a tangent line, couldn't we? Because we know how to find the gradient of a line. We've learned all that. So we could draw a tangent line and we could calculate the change in y or the change in x. The problem is, where would we draw it? You try and put your ruler on there and the ruler could sort of slip that way or that way. It ain't going to work. It isn't going to give us anything meaningful. So our old ways of changing y, of changing x are, actually we do still use, but it doesn't look the same. So back to our question, how on earth do we do it? So supposing we want to find the gradient of a cost function, let's say q equals 100. Suppose we want to find marginal cost at the point where q equals 100. So how are we going to find that gradient? Well, you've probably guessed, we're going to differentiate the cost function. So we can differentiate, whatever that means, the cost function and find the rate at which cost is changing at any point on the curve. It is so immensely powerful. So the result of differentiating, and I haven't told you how you do it yet, is another function. So out of this differentiation process comes another function. And the name of the function, depending on what we're differentiating, is either dy by dx, dc by dq, dq by dl. This looks like we've differentiated a production function with respect to labour. This looks like we've differentiated a cost function with respect to quantity. That's just a vanilla dy by dx. from a graph. And these functions are called derivatives. So when we differentiate a function, we have that underlying function, but we also have the derivative of that function. And they're also called the gradient function because they're magical functions. They're functions such that they will tell you the gradient at any point on the curve. It's so mind-bogglingly useful. So by differentiating the cost function, we get dc by dq. There's always two letters, c and q. And so what this is telling us is what tiny change in cost we get from increasing quantity by 1. So it's still that idea of the rate of change of one variable as the other increases by 1. So the one on the bottom is always the one that's increasing just by 1. So this will truly give us marginal cost, how much cost changes as quantity increases by 1. Okay, so let's suppose that we have differentiated cost. We've got this mysterious thing called dc by dq, which is going to give us marginal cost. And supposing the dc by dq function looks like this, well, we can use that to find the gradient of any point just by substituting in the value of q. So if we're interested at marginal cost when q is 50, then we substitute 50. Here we're interested in, I don't know, 100, so we can substitute in 100. But the point is, by substituting any value of q, we can find the marginal cost at that point. So when q is 4, say marginal cost is going to be 3 plus 10 times 4, which will be 43. But when q is 80, it can still tell us the answer. Marginal cost will be 3 plus 10 times 80. So in total, 803. So you see, it's a sort of surgical precision. We can ask for the marginal cost at any point on that curve. How cool is that? And it just seemed a bit like a miracle. Yeah, that's exactly what differentiation feels like. But you'll see that the actual mechanism of differentiating is very, very easy. So I want to finish by just giving you a sense or a feel for how differential calculus works, because it's this amazing piece of intellectual thinking. And the idea is breaking a problem down into ever smaller parts and taking the smallness to a limit so that we are dealing with infinitesimally small things. And let me just give you an example of it, because you don't need to know how to do this from first principles, but let's use it. Let's use the calculus method to solve a problem that you'd be very familiar with. Let's suppose we want to prove that the Greeks were right and that the area of a circle is indeed pi r squared. And let's say all we have to work with here for this problem is that we know the radius is r, halfway across radius, and we're reminded that the length outside is 2 pi r, the circumference is 2 pi r. And sort of by extension, halfway round is pi r. So half of the distance around is pi r. So starting to think about our calculus method, we're going to chop it down into smaller parts. Let's first start by having 4 parts to our circle. And hopefully we can see that these straight lengths are radiuses, radii. Yeah. So that's r. And halfway round the circle is pi r, as agreed. So there it is. But what happens if we take smaller slices? Well, it's still pi r. That's still half the distance around the circle. That's still r for radius. Let's take even smaller ones. Yep, still pi r, still r. And now we start taking it to the limit. We start making these slices infinitesimally small. And look what happens. In fact, if we take it to the absolute limit, they become so tiny, they just become straight lines. So they just merge into each other. And this is what happens with our gradients. Yeah, so it's still r, pi r. We know the area of a rectangle is base times height. So in this case, it's pi r times r, which is pi r squared. So it turned out that the ancient Greeks were right. So that's just a sense of how this calculus works. So finally then, how do we use it to find the gradient of a curve? Well, we take 2 points on the curve. We can find the gradient of any straight line joining 2 parts, because it's just a straight line, difference of y and difference of x. But what we're going to do is take it down by steps, and we're going to take those steps to be infinitesimally small to the extent that b is really now a, and find the gradient at that point. So I know that won't make a lot of sense, but anyway, that's how it works. And I look forward to showing you how to actually do it, which is much easier. Okay, I hope that was helpful.